Welcome to a guide to Lab 1. We're going to show you real quickly kind of the process you're going to follow. I'm going to show you a different geometry than the one that you'll do, somewhat more complex geometry, but also a truss. And I will, not a lot of commentary here, just try to show you the basic process of what needs to happen. So when you open Workbench, you'll get to this page and you'll have a series of analysis types that are set up over here. And to use one of those, you just click on it and drag it into the schematic. At this point, you see a series of cells that have different parts of the model. Engineering data is already filled in with a default material, structural steel is what they're calling it. We're going to leave that as it is. For the geometry, you can create your geometry in here. You can import it from a CAD model. In this case, we're just going to import geometry that was already created for you. This you will download from Learning Suite. So I'm going to come in and browse. We're going to pick this more complex truss. Now at this point you could go on with it, or you could double click on geometry and open up the space claim to be able to see your geometry and edit the geometry. But that is covered in a separate video, how to do the editing you will need to the cross-section. So let's go directly to the model. You see that that's green now. So I'm going to double click on model, or you can do right click and select edit. This will open the Ansys mechanical. Okay, so the model came in, it's a beam model, and so it's represented by lines, and then there are cross sections. And so again, you can see geometry, a bunch of lines, which I named to help me remember which one is which. And these can also be grouped into components. We have the material, we have our cross section, in this case a rectangle that's assigned to it. If I want to change that, I can do that back in Space Claim. And then we have sections for connections and the mesh. Now in order for this to operate, I need to tell it how it interacts with the world and how the different beams interact with each other. First, let me orient this so that I'm looking at it straight on. So I'll click on the axis there. A good way to proceed with these is to start from the top down. And we see the green checks by each of these boxes that show that they're ready. Now, connections says that it's ready, but there's nothing in there. And in actuality, it doesn't know how these beams are going to interact with each other, and so it won't be able to successfully analyze the truss. So we're going to go and insert connections. So insert, and what we want to do is a joint between the two different beams. So I'll insert a joint. It's going to default to fixed, meaning there's no rotation or translation allowed between the ends. I'm going to select revolute, as that's the basic assumption that we make for finite element analysis. Now, one of the values of the finite element analysis is I can go and test what the impact of relaxing that assumption is and maybe change it to fixed. That might be something you want to explore in the latter part of the project. But initially we'll take revolute, and we need to pick the ends, the vertices of that part. So I'm going to come up here and select vertex, and I will click, and there's a double selection. Now I just want to have these two connected to each other, so it doesn't matter which one is which. So I'm going to hit apply, and then I'll come down and select the second one. And now I'll click this second square, rectangle, that will select the second one, and I'll hit apply, and I've created my first one. Now I can then proceed and insert another joint, and I like to work methodically, so I'll come up here and I'm going to select this next one, and I'll go ahead and select the first one, and then I can come down the bottom and I'll select the second, apply, and again I can see that I fixed AB, which is what I call this one, to BC. And that's a fixed one. Let's go ahead and change that to a revolute joint. Now I need to also connect the other arm of that, so I can go and insert another joint So we'll change that to revolute. And that's selected, so I pick second, scroll down here, I'll pick the third one, apply. You have to make sure you hit the apply in order for it to do that. And I see it's BC to BG, so it's BC to BG. And so this is connected, these two are connected, and then this one's connected to that, so it'll be adequate. And I need to go around and do each of these joints. So I had to do 2 joints to find this one. I'll have to do 3 because there are 4 members, and 2, 1, 3 there, and 3 there. So rather than show you all that, I'll go ahead and just show you one other thing that you can do is I could group these. So if I said, well, these 2 are both part of the same joint, so I could group them, and I could put a name by that. So I could say top right. All right, so that'll help me see which one is which if I'm trying to find a particular joint. You can also rename a specific joint, but I'm going to go ahead and leave this one as is. Okay, so I've now created all of the joints. You can see they're in several different groups, and I've named them to help me keep track of them. And it also incorporates the names of the parts, and so that's why also in the model the individual beams are renamed. The next step, if we go down there, is to create the mesh. So we can go ahead, if we right-click on there, we see that lightning mode, it means it needs to be generated. To generate the mesh, this meshes very quickly. For this type of mesh, it's not very sensitive to the number of elements. I'm just going to set that mesh and go forward, though generally we do want to take some care with our mesh. Now I can come down to analysis settings. These are parameters that may be set to help define the solution. And I see that my solution has question marks. There's a few things that need to be resolved. Specifically, I haven't said how this relates to the world. I need to tell the program where it's supported and where the forces are. So if I want to support that, I could put a fixed support. Actually, I'm going to prefer, delete that. I prefer to put in, apply a displacement. And I will come and select my vertices, select the vertice. And again, since those are linked together, it doesn't matter which one I select. I'll hit apply, and then I will set my X displacement, Y displacement, and 0 displacement to 0. And it's important you get the Z too. Even though we don't expect any loads, the solution may be unstable without that. And so it's good practice to constrain it in all the dimensions. It may also, to that extent, be helpful to have some rotation constraint. So let me put so let's insert supports a fixed rotation, and I'm going to make the X free so that they can rotate there. But I shouldn't expect to see any rotation around the Y, around the Z. So anything around the Z would be unexpected. Now this would be something you may want to explore later to see the impact of these settings. Okay. Now I need to constrain the right side. So I'll put a support, apply displacement, and there to represent a pinned condition, I would want to have the X free, and then I will set 0 for Y. Oh, and I need to select my geometry, so I'll come over, click that, and hit apply. So now I've constrained that. And now I need to apply the exterior loads. So you see there's a variety of loading types that can be applied here. Let's go ahead and apply a force, and we'll select the node, hit apply, and then I'm going to select, I can do a vector, which allows me to do magnitude, do minus 50, minus 40,000 newtons. And I could pick a direction, but I think it'll be easier, particularly in this case, rather than selecting geometry. Well, instead of doing a vector method, is we'll do it by components. And so I could just pick Y there, and change my, lost my number. Oh, that's for P for parameter. You don't want to set that at this stage. We will show you how you could use that later on. Otherwise, it's just going to make it a little harder to change things. So set that to 40,000. So I've got my applied loads. I have my simple is supported cross section, and a rotation just to help things be stable. Now I'm ready to solve because I've got green. Oh, I didn't select a geometry there. You notice there's a question mark next to fixed rotation, which says that it's not, it hasn't been, there's some unknown, something missing. So I need to set that. So let me come over here and select that node and hit apply. Now I could go ahead and solve it, but I wouldn't be able to see anything. What I need to do is tell it what kinds of plots I want to create. So one of the things I can do is there's a tool, and we'll select the beam tool, and that's going to set in a couple of default types of plots. And then I can add some additional ones. So I could pick a deformation. I also might want to put in some beam results like the axial forces. And now when I run this, hit solve, you see it goes to green, lightning bolts, it's working on it. And if all successful, we'll get green check marks. All right, so now we can click and we can look at these. And I can change the magnitude of the deformations by selecting the scale up here, so true scale or various levels of amplification. One of the things that may be helpful here, one of the things you want to look for here is to see if things are deforming as you might expect it to. This is coming down. We have some bow in here. If we plot the stresses, we notice that these are close to 0. You might ask yourself whether that's what you would expect. And eventually you do hand calculations to verify many of these things. Now that's the basic solution. It gives us stresses, and we can deformations in the structure. We could get axial force. Now, but this does not account, we have a lot of compressive stress, particularly in these members across the top, and this doesn't consider whether those members might buckle. So let's look at how we could consider buckling in our solution. So I'm going to go ahead and close this Ansys Mechanical, so we go back to the Workbench tab. Down here, there is at the top eigenvalue buckling. So if I drag that, I come over here, I'm going to just set that down on top of the model, and it's going to tell me I want to share the data between those, and it's going to automatically draw these. I could do it manually, but this is easier. Now I also need to know the loading type, and I can grab that from the solution, and I drag that across to the setup, and we see it wires those across. And I've already got green arrows down here, and this one's ready to go. So let me double click on that, and we'll reopen Ansys Mechanical so we can configure the rest of the analysis. So here we are back in Ansys Mechanical, and we see that all of the information we had up here is there. The connections are collapsed, but they're still there. But we had added an additional section, and so and we can work with both of them here now. We can see that this says it's ready to grow. I have some analysis settings. There's one thing I want to change here is the number of modes. This is essentially eigenvalue calculation, and so it's how many do I want to get, and it'll start with the lowest force and go up. But I'll go ahead and pick a couple of them. Usually the first one or two should be adequate and tell you what you need to know. Another parameter here to look at is the negative load multiplier. It's going to find the buckling loads in terms of fractions of the applied load. And it's going to consider both positive and negative. If I only want to consider the case of loads being applied the direction they already are, in this case they're down, it's a negative load, so a negative multiplier would mean buckling from an upward load. If I don't expect those, then I could set this to no, and I'm going to go ahead and do that on this case. And by way of solutions, the big thing I'm looking at is the shape of the deformation. And so let me insert a total deformation. And you can see that's for a specific mode. So what I want to do is create a new one for each mode. So I'll copy and paste, paste, and paste. So I have 4 of those. So I can come in and click on this, change that to 2, change that one to 3, change that one to 4. Now I could go ahead and solve. Okay, so I click on that and I can see my deformations. And you see it's kind of buckling out of the plane there. Kind of makes sense. If we look on the multiplier, it said it's buckling right at 1 times the load. So I'm at my buckling limit, is what it's telling me. Not a great place that I want to be. I'd like to have a higher load. If we click on these others, we can see that they're buckling at higher loads. So really it is this first one I need to worry about. And so that's the process for doing a static and a buckling analysis on the truss.